Okay, so I'm gonna review what we learned about free body diagrams in the previous session quickly because these guys are so important that you need to feel very comfortable with drawing a free body diagrams and how to apply the equations using the free body diagram before like you want to learn other stuff. So when we solve problems involving forces and Newton's laws, it's essential to begin by making a sketch that indicates each and every external force acting on a given object. Now, this type of sketch we called free body diagram. And then the steps involved in constructing such a free body diagram are, first of all, sketch the forces, sketch the forces. So you're going to identify and sketch all the external forces acting on an object. So external forces. Sketching the forces roughly to scale will help in estimating the direction and magnitude of the net force. So for example, if you know that the weight is more than the normal force, then you're going to draw a larger arrow. And then the next step is to isolate the object of interest. All right. So this means that you're going to replace the object with a point particle of the same mass and then apply each of the forces acting on the object to that point. For example, if you have a box that is hanging from the ceiling, right? So the normal sketch will look something like this. So there is a box that is hang. Okay, so when I want to draw the free body diagram, then what I'm going to do is that instead of a box, I'm going to put a point, and then I'm going to sketch the weight, which is one force, and the tension of the rope. Now, if I already know that the tension force is less than the weight of the box, then I'm going to make this tension arrow to be smaller. And then choose a convenient coordinate system. Choose a convenient coordinate system. So depending on how you like to, it has three. Okay, so that was M and N. Depending of how you want to solve the problems, totally up to you how to choose a coordinate system. But of course, the logics say that it's better to use the most convenient coordinate system. For example, if I'm just having a system that has forces in y direction, so it's the best if I choose my coordinate system to be here 0 and then positive y, for example. And then resolve the forces into components. Okay, resolve the forces into components. And this is very, very, very important. Now, if you have only forces in one dimension, your life is easy. But if you have forces that have two dimensions or three dimensions, then the best is to resolve the forces into their components and then treat each of them or each direction separately. So when it comes to the second Newton's law, which is F equals to ma, if you have two dimensions, it's better to write F in x direction equals to m ax, and then this is the summation of forces, and the summation of forces in y direction equals to m times ay. And then this was the last step. Apply Newton's second law to each coordinate system, which is what I just did. Okay, so this guy here. Now I want you to have your book in front of you and take a look at figure 5.7 on your book. All right, so you can see that here the basic steps of like free body diagram is illustrated. Now, if you can see in part A of the figure, it says sketch the forces. So the guy is just pushing the couch, all right? And then there is the couch and a pillow on the couch. Okay, so he's applying external force F, and then we know that the couch has a weight. Okay, so the object of interest is the couch. Now, if you want to isolate the object of interest, so you're not going to consider the guy anymore, the pillow on the couch does not matter anymore because the object of interest is the couch. So you just show it by a point. And then there is this external force that is being exerted on the couch. So you do not need to consider the guy anymore because the force is exerted on the couch. Okay, so out from that point that resembles the couch, then you are going to sketch the weight arrow, the external force arrow, and then the normal to the surface. And in part C, you can see that it says choose a convenient coordinate system. So the book has considered the typical X and Y axis. And then it has resolved the forces into its component and then applied the Newton's second law to each component separately. In some problems, we are giving information that allows us to calculate an object's acceleration using the kinematics equations, the ones that we studied in chapter 2 and 4. Now, once the acceleration is known, the second law can be used to find the net force that caused the acceleration. For example, suppose an astronaut uses a jetpack to push a satellite toward the space shuttle. These jetpacks, which are known to NASA as manned maneuvering units or MMUs, man maneuvering units, MMUs, are basically small one-person rockets strapped to the back of an astronaut's spacesuit. Okay, so 1 MMU contains pressurized nitrogen gas that can be released through varying combination of 24 nozzles spaced around the unit, producing a force of about 10 pounds. Okay, so, sorry for this really ugly figure here that I sketched for you. Okay, supposedly this guy is an astronaut that is pushing in this direction a 655 kilogram satellite. So the mass of satellite is 655 kilograms. Okay, so if I want to sketch the free body diagram for the satellite, I'm gonna sketch it something like this. So instead of the satellite, I only will have a point, and the only force acting on it is the external force that the astronaut is exerting on it. Okay, now next, we're gonna choose the convenient coordinate system. So it's more convenient for me to just consider the coordinate system like this. And this is the origin. Okay. So the x-axis point in the direction of the push. Now, if the satellite starts at rest, okay, start at rest, it means that V naught is 0 and moves to x equals to 0.675 meters after 5 seconds of pushing. What is the force F exerted on it by the astronaut? Now, what is F? All right, so let's just consider that x naught is 0. So I put the origin exactly at the time 0. Okay. Now, I know that the equation for kinematics is x equal to x naught plus v naught x in t direction plus half a in x direction t squared. This guy is 0, this guy here is 0. So I have x equals to half ax t squared. All right, so from here I can find acceleration to be 2x divided by t squared, meaning acceleration is going to be 2 times 0.675 meters divided by 5 seconds squared. So this means that the acceleration is going to be 0.0540 meters per second squared. Okay, so this is my A. Now that the kinematics has provided the acceleration, then I can use the x component of the second law to find the force. Now, only one force acts on the satellite, and that is the x component of F. So I can write the summation of all forces in x direction equals to F equals to MAX. So I'm going to just multiply 655 kilograms by 0.0540 meters per second squared, and then F is going to be 35.4. You know that the unit for force is Newton, and then obviously it is in the positive x direction because that is the only force. Another example is example 5.4, the force exerted by foamcrete. So foamcrete is a substance designed to stop an airplane that has run off the end of a runway without causing injury to passengers. It is solid enough to support a car, but it crumbles under the weight of a large airplane. Okay, so that is the figure 510 on your book. By crumbling, foamcrete slows the plane to a safe stop. Okay, for example, suppose a 747 jetliner with a mass of, so here the problem starts to give us the known of the problems. So the mass of 1.75 times 10 to the power of 5 kilogram and an initial speed of 26.8 meter per second. Okay, so the initial speed is 26.8 meters per second, is slowed to a stop in 122 meters. So x equals to 122 meters. What is the magnitude of the retarding force exerted by the foamcrete on the plane? Okay, so here again, I want to find F. What is it? All right, so if I want to sketch this, so I know that at first, airplane is here. So this is an airplane, hopefully. Okay, and then it has the initial speed of V naught, right? And then the foamcrete happens here, and it takes 122 meters for it to make the airplane stop, 122 meters is my delta x. If I just set the coordinate system at 0 right here, okay, so like this is my coordinate system. Okay, so when the airplane stops, now the airplane is here, okay. This means that v is 0 here. So the final v is going to 0 because it is stopping. Okay, now the retarding force is going to act in opposite way, right? Because the airplane is going forward, so we need a force to make it stop. So that is in opposite direction. So I can instantly write F to be a negative something, let's call it small f, x direction. So it is in negative x direction. Okay. So first of all, I need to find acceleration so that I can use that to find force. Okay, so I'm going to use this equation. V squared minus V naught squared equals to 2ax delta x. And all these guys are in x direction because I do not have a y direction at all. So it means that my acceleration is V squared minus V naught squared divided by 2, delta x. So ax is going to be 0 minus 26.8 meters per second squared divided by 2 times 122 meters. So the acceleration is going to be negative 2.94 meters per second squared. Okay, so all the forces that I have in x direction, so you remember and you have studied that this guy here, it's the summation. So everything is negative f. Okay, so this means that the summation, which is in negative f, equals to m a sub x. Or I can write that f is negative m a x. These two guys are equal, right? So I can find f to be negative 1.75 times 10 to the power of 5 kilograms times negative 2.94 meters per second squared, and then that force is 5.15 times 10 to the power of 5 newtons. Okay, so this is the magnitude of force, but then direction is in negative x direction, so I can write this is negative 5.15 times 10 to the power of 5 newtons x hat. This means that, or you can write it to be 5.15 times 10 to the power of 5 newtons in negative x hat direction. So these guys, they're both equal. And finally, we are here talking about Newton's third and last law of motion. So your book states that nature never produces just one force at a time. Forces always come in pairs. Okay, so forces always come in pairs. In addition, the forces in a pair always act on different objects and are equal in magnitude and point in opposite directions. Okay, so the forces in a pair always act on different objects. They are equal in magnitude and point in the opposite direction. All right, so with this, Newton's third law, and this is the law itself, states that for every force that acts on an object, there is a reaction force acting on a different object that is equal in magnitude and opposite in direction. Okay, this is very important that you guys know how the different Newton's law of motion are stated. Okay, so in somewhat more specific form, we can say that if object 1 exerts a force F on object 2, so let's say this is box 1 and this is box 2. If object 1 exert this force on box 2, F, that is being exerted by 1, then object 2 exerts a force negative F on object 1, which is exactly equal but in opposite direction. So this is the 1 on 2 and this is the 2 on 1. Okay, now in abbreviation, instead of this law, we usually say that for every action there is an equal and opposite reaction. Okay, so this is like the more common state of it. Okay, now this happens in many stuff around us in the daily life. Okay, so this action reaction pairs happens everywhere. For example, I'm sitting on a chair right now. I'm pushing the chair down and the chair is pushing me up. That is funny, huh? Because if the chair is pushing me up, why am I not floating on the air? It's because my weight is balancing that push up from the chair. Try to push your hand on the table really hard. You feel it, like you feel that the table is pushing your hand up, and that is actually what happens. You push the table down, the table push your hand up. But again, there is another force that is balancing this, that is called the weight of your hand and the weight of the table, and that is why nothing is floating. Okay, for example, if this person here, again, my nice drawing, when I say a person, if this person, and these are the arms, poor guy, okay, if this person is pushing this heavy box in this direction, so the box is pushing the person with exactly the same force, magnitude wise the same, but in opposite direction. Okay, now if you look at figure 515, that figure illustrates some action-reaction pairs, and I want you to notice that there is always a reaction force, whether the reaction force is push or it's pull or anything, like any type of force, then there is a reaction pair, or there is a reaction force that makes a pair with the original force. Okay, for example, when the Earth exerts a downward gravitational force on the space shuttle, the shuttle exerts an equal and opposite upward gravitational force on the Earth. All right, that is true because the Earth is so much heavier, then the Earth does not notice any difference. But for the smaller object, that matters. For example, if there is a truck that is moving and a mosquito hits the truck windshield, then the truck pushes or exerts a force on a mosquito, and the mosquito actually exerts the similar force on the truck, but because the mosquito is like way less mass, it has way less mass, then the mosquito is going to die, but the truck doesn't, like nothing happens to the truck. Now if you replace the mosquito with a bigger stone, then you can see the effect, because now we're talking about a much bigger mass. Another thing is that the third law, forces act on different objects. So this is important to know, that the third law, forces, or when we say like the action reaction forces, they act on different objects. Okay, this means that these action reaction forces always act on different objects. Okay, so when we are drawing a free body diagram, we only draw one of the action reaction pair forces. The other force in the pair would appear in the free body diagram of a different object. So that is the reason that the two forces do not cancel each other in the free body diagram, because they're acting on different objects. Okay, as an example, I'm going to solve example 5, 6, just to clarify this. And that is that the two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. All right, so I have two canoes here. So let's call this 1, and then let's call the other one 2. All right, so what happens here is that a person in canoe 1, these are the long arms of this person. Okay, so he's going to push the force of 46 newtons to separate the canoes. Okay, so he's going to push this canoe to separate this. Now, the mass of canoe 1 and its occupants is M1 is 150 kilograms. And then the mass of canoe 2 is 250 kilograms. Now we want to find the acceleration the push gives to each canoe. Okay, so in part A, you're going to find the acceleration that this push is given to each canoe. Okay, so what I'm going to do here is I'm going to name this F2, meaning that the force that is being given to 2, and then I am going to write F2. First of all, it is in positive x direction, and the problem says it is 46 newtons in positive x direction. Okay, so according to Newton's third law, there is an equal but in opposite direction force that is being exerted on the first canoe. So let's call this F1, and then I know that F1 is 46 newtons in negative x hat direction. Okay, all right, now for the convenience I can just put the x-axis in this direction but choose the origin in the middle. Okay, so this is my origin. Now I'm going to draw a free body diagram for each canoe separately. So for canoe number 1, I have the weight of the canoe, I have the normal force of the canoe, and I have the force on the canoe, and that is the reaction force. Now for canoe number 2, I have its weight, I have its normal force, and you should know by now that everything that is placed on any surface, it has a normal force from the surface. And then I have F2, which was the external force. All right. Now, for the acceleration, okay, the very first thing that I want to actually here emphasize is that the normal and the weight cancels because they are equal but in opposite direction, right? Otherwise, either the canoe would sink or it would float or it would just like fly on the earth. All right. So the only forces that is left in x direction is the forces that are external because of the pushing of that person. So I can write that for the first canoe, I can write that F in the first boat or the first canoe in x direction, the summation is going to be m1 times acceleration of canoe 1 in x direction. So from here, I can find acceleration of the first canoe in x direction to be, okay, F1 is negative 46 newtons, right, because in a negative direction, divided by 150 kilograms. So it is going to have a negative acceleration, meaning it's like going to accelerate in negative direction, negative 0.31 meters per second squared. Okay, so this is for the first one. Canoe number 2, I can write the same thing, that for the canoe number 2, F in x direction is m2 times a2 in x direction. So I can find the acceleration of canoe number 2 to be 46 newtons, with them positive, divided by 250 kilograms. Now you can see how the mass actually affects the acceleration, right? Now this canoe is heavier, so it's going to accelerate less. So it's going to accelerate 0.18 meters per second squared. And actually this is a very logical result, because if something is heavier, it's just like it's more difficult to move it. In part B of this problem, it asks us what is the separation of the canoe after time equals 1.2 seconds of pushing. So if that person keeps pushing the canoe for 1.2 seconds, what is the separation of it? Okay, so the separation means that delta x. So what I'm going to do is that I'm gonna write the kinematic equations related to position and time. So I'm gonna use x equals to x naught plus v naught x direction times t plus half ax t squared. All right. So because I put the origin to be in the middle, I can just, just consider that is my 0. And then I want to find the position of canoe number 2 after 1.2 seconds. So I can just consider that x naught is 0 because that is where my origin is. And then at the beginning, it doesn't have any velocity. Okay, so these two guys here, they are 0. So I can only write that x, let's just put it sub 2 here, or give it as subscript 2 to show that that is for canoe number 2, is half a2x t squared. Okay, so the position after that 1.2 seconds is half, the acceleration was 0.18 meters per second squared times 1.2 second squared. So x for canoe number 2 is going to be 0.13 meters. Okay, so this is after 1.2 seconds. Now, I want the separation between the canoes, so I need to find the position of each canoe after 1.2 seconds. So I'm going to use the same for canoe number 1. So canoe number 1 is going to be half a1 in x direction t squared. But then the only thing that is different here is the acceleration. It's going to be half negative 0.31 meters per second squared times 1.2 second squared. So x1 is going to be negative 0.22 meters. Okay, and then delta x is x2 minus x1. That is like the difference between them. So it is 0.13 meters minus negative 0.22 meters. So the separation will be 0.35 meters.